Hello, welcome back to the channel. So let's do one more question on numerical integration. And in this question, we have to use Simpson's rule to approximate log2 using this integral over here. So we know that if we solve this integral over here, the integral of 1 by x is log x. And if we plug in the endpoints and calculate the definite integral, we'll get the log 2 at the end, right? Because we know that log 1 is 0. So now, instead of solving this integral, we have to use numerical integration in order to approximate log 2 using Simpson's rule. So it is basically the same process and the same formula that you use in order to approximate integrals, the definite integrals using Simpson's rule. But before doing that, we know that we'll have to calculate a, b, and delta x so that we can use those values in order to calculate the Simpson's rule approximation. So we can clearly notice over here that our a is equal to 1, our b is equal to 2, which is our lower and upper endpoints, and our n is equal to 6 because we are using 6 subintervals, so n is equal to 6. Now if we want to calculate delta x, it would simply be b minus a over n. b is 2, a is 1, n is 6, so our delta x is equal to 1 by 6 in this case, right? So now we know that for the Simpson's rule, we calculate our fxi's, where every xi is given by a plus I delta x formula, right? And we also know that we start from x0 all the way to our xn by taking increments of delta x in these type of cases, right? So we've already covered these concepts in detail in the last videos. So if you have not watched my previous videos on Simpson's rule approximation, I would highly suggest you to first watch those videos in order to get the full context of this video, because in this video we will be going over these concepts quickly and solve these questions over here. So now, based on this given information, we can easily use Simpson's rule with 6 subintervals to approximate log2, or in other terms to approximate this definite integral over here. And if we approximate this definite integral over here, we can simply use this formula over here, which is the formula for the Simpson's rule. So we know that for the Simpson's rule calculation, we multiply our inner expression with delta x by 3 first. So we know that our delta x is 1 by 6 in this case. So delta x by 3 would be 1 by 18. And now you know that you start with x of 0. So x0 would be simply a, because if you substitute I as 0, you'll get a. So you'll start from a and then end at b by incrementing 1 by 6 by incrementing delta x for your next terms, right? And you also know that in the Simpson's rule, for the inner bracket, the first and the last terms have coefficient 1, and then for the middle terms, you have an alternating sequence of 4 and 2's, right? So now based on all this information that you already know about the Simpson's rule, you can easily calculate or approximate log2 in this case, right? And if you solve this expression over here, you'll approximate your log2 to be this value over here, which would be using Simpson's rule and not using the theoretical integration that we already know, right? So I hope that makes sense. Now let's move on to the next part. So the next part is about calculating the value of the subintervals which would be required in order to guarantee the absolute error to be less than 0.00001 in this case. So now, since we have already calculated such type of questions in the previous videos as well, we know the process in order to calculate these questions. So first we'll have to calculate the value of L, which would be the upper bound of the absolute value of the fourth derivative of f of x. In this case, our f of x is 1 by x. So if we proceed on calculating the fourth derivative of f of x, where our f of x is 1 by x, we know that our f dash x is minus 1 by x square. If we calculate our second derivative of f of x, it would be simply 2 upon x cube. Third derivative would be minus 6 upon x to the power 4. And then fourth derivative, in this case, which is what we are concerned with, would be simply 24 upon x to the power 5 in this case, right? So now you calculated the fourth derivative of f of x, and now since we are only concerned with the absolute value of the fourth derivative of f of x, so if we take the absolute value on both sides, we have to calculate the maximum value of this expression over here in order to calculate the value of capital L, right? And that maximum value should be the maximum value which is between the x interval. So we know that since our x is varying from 1 to 2, since our x is varying from 1 to 2, we know that this expression is a decreasing function, right? So the maximum value would be when x is the smallest, which is at x equals 1 based on this interval. So we know that when x is equal to 1, this expression has the highest value. And when our x is equal to 1, when our x is equal to 1, our f of our fourth derivative of f of x is basically 24. And this is also the value of L in this case, because we know that in order to calculate the value of L using Simpson's rule, we get an upper bound for the absolute value of the fourth derivative of f of x, which was calculated to be this expression over here, right? So now we have solved for our value of L. We know all these values except the value of n which we are calculating, and we also know that this error should be less than this value over here. So if we proceed on calculating that, we know that we have this formula over here. So the formula is basically L times b minus a to the power 5. So L times b minus a to the power 5 upon 180 n to the power 4 over here, right? And we know that this error should be less than 10 to the power minus 5 in this case, right? This is 10 to the power minus 5. So this error should be less than 10 to the power minus 5 in this case. So if this expression should be less than 10 to the power minus 5, let's plug in all the values. And when you'll plug in all the values, you know that in this case, L is 24, B is 2, A is 1, which we already calculated before. This is 180 and we are calculating, and this should be less than 10 raised to the power minus 5. And now if you'll proceed on calculating this inequality over here, it will be simplified to this expression over here, and you know that this should be less than 10 to the power minus 5. And then if you'll calculate your n by solving this inequality, you'll get your n to be greater than equal to 10.7 in this case. And there is one very important point about the Simpson's rule approximation, that the number of subintervals should always be even. And we also know a second property of subintervals, that they should be a whole number, right? So basically, if I have to sum it all, in Simpson's rule, our n should be even and it should also be a whole number. So in this case, we have to pick a whole number which is even and is also greater than equal to 10.7. So the next even number which comes after 10.7 is 12. So that is why in this case, if we have any even number which is greater than or equal to 12, we will guarantee that the absolute error in this case is less than 10 to the power negative 5 in this case. So that's it for this video. Again, we used the same concepts that we covered in the last videos. This was a combination problem in which we covered both the approximation and also calculating the error bound. But the main takeaway from this video is that whenever you're calculating the number of subintervals for the Simpson's rule, specifically, you have to make sure that whatever n you get after solving the inequality should be a whole number, and it should also be an even number, because in Simpson's rule, your number of subintervals should always be even. So feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye-bye. Take care.